A couple M equal to 20 kilonewton act on the end of a slender steel cantilever beam having Young modulus equal to 210 gigapascal to bend it into an arc of a circle of radius r. As shown in the figure, the cross section of the beam is a square cross section of diameter d equal to 120 mm. Calculate the maximum tensile stress in the beam, calculate the radius of curvature of the beam, and calculate the maximum deflection of the beam if its length is equal to L is equal to 4 meter. So we have initially here a slender rod, and this slender beam is a horizontal having a cross section equal to square cross section with the dimension d is equal to 120 mm. And by applying a couple here, that is a sagging, in this case we can turn the bar here about the fixed end, and we have shown here the new position as shown here by this red color. We have to find out here what is the maximum tensile stress developed in this case and what is the radius of curvature. Radius of curvature we can find out here from extending this vertical through this point and extending the edge view, and where it will intersect, that will be our center of curvature, and then you can measure the radius of curvature. So let's draw here a vertical line at the fixed end. So this one is a vertical line drawn at a fixed end, and this edge will extend. Where they will meet, that will be the center of curvature. So somewhere they will meet here. So this one is point C, and point C represents here the center of curvature. And we have to show here a dotted line. This dotted line represents here the neutral axis, and if you measure the distance of the neutral axis from center of curvature, then we have to find out the value of radius of curvature rho. That is the second part. Secondly, it's a rectangular section whose dimension is equal to 120 by 120. So we have a rectangular section here. We have width is same as equal to depth is same as equal to 120 mm. We can very well locate here the centroid location, and the centroid location here is represented by G. In that case, we have horizontal axis is X and the vertical axis is Y. So the maximum stress will be on the top fiber, and for top fiber we have value of Y will be same as equal to D by 2. Whereas for bottom fiber also we have a maximum value of the stress will possible, so that Y is equal to D by 2. So one value of the maximum bending stress you have to calculate. And third case, we have to calculate the maximum deflection of the beam. So we need to calculate the value of delta max also. So these are the requirement for us. One is a bending stress, one is a delta max, one is the radius of curvature. Value of M is given to us. Since we have a sagging here, we have M value will be taken as positive, and we have positive value of M is equal to 20 kilonewton meter. Remember here we have to calculate the maximum tensile stress. The top fiber is shortened and the bottom fiber, the length has been increased. The top fiber will be in compression and the bottom fiber will be in tension. In addition to this, he has given the value of Young modulus, which is equal to 210 gigapascal. 210 gigapascal. Length L is also given, that equal to 4 meter. So we have length equal to 4 meter. Here the value of M is given, value of E is also known, and for square section we have I is equal to D to the power 4 by 12. So we can very well calculate here the value of rho. For this one we'll use the flexure formula. The first term in the flexure formula is bending moment M divided by I is equal to Young modulus divided by the radius of curvature rho. So we have radius of curvature rho is same as Young modulus multiplied by moment of inertia I divided by bending moment M. Young modulus here is given as 210 gigapascal, so you have to use that value in megapascal. Is 210 into 10 to the power 3. For square section we have D to the power 4 by 12. We have value of D is equal to 120, so we have 120 to the power 4 divided by 12. And kilo you have to multiply by 1000, and meter to convert into mm, again you have to multiply by 1000. So we have bending moment equal to 20 into 10 to the power 6. That will be Newton mm. So the radius of curvature in this case will be come out close to 181.4 into 10 to the power 3. That will be mm. So is same as equal to 181.4. That will be meter. So it's supposed to be very large radial distance. And already we have told you in the theory also that the dimensions of a section is negligible as compared to the radius of curvature. So this value of rho is very greater than the dimension of a cross section. Either we can say D or we can say B. So first part is answered, that is the radius of curvature is known. In this case the top fiber is in compression and bottom fiber in tension. Suppose I show the stress distribution, that we have tensile stress on the bottom fiber is a maximum value and the compressive stress on the top fiber, and we have same value of C. So this point is same as our neutral axis, and this value is same as C is equal to D divided by 2. So again we'll use here flexure formula, that is we have M divided by I is same as equal to sigma B maximum divided by C. We have maximum value of a bending stress, that is sigma B maximum is same as equal to M multiplied by C divided by I. Bending moment here is 20. So we have 20 into 10 to the power 6. Value of C is D by 2 and we have D is equal to 120. So we have 120 divided by 2. Moment of inertia is same as D to the power 4 by 12. So we have 120 to the power 4 and is divided by 12. In this fashion we can calculate the maximum bending stress. The maximum bending stress will come out to be 69.44. That will be megapascal. And one value we have to calculate is the delta max. Now we want to calculate the value of delta max here. For that one you have to do the little calculation. This one is the same as the radius of curvature. So from C to point A, we have radius of curvature is equal to rho. This one is also radius of curvature equal to rho. Let's say this angle formed here is equal to theta angle, and we'll draw here horizontal line from the point B. So let's say here this point is B point, and this B point will meet to the vertical at point D. Now we have formed here a right angle triangle, and in this right angle triangle we are able to calculate the value of theta here. Once we calculate the value of theta, we can calculate the vertical length equal to CD, and then we have rho minus CD will be same as equal to delta max. So this length here is approximated as same as equal to L, because the angle form is very small angle here, and this length is same as equal to 4 meter. Radius we'll use here in meter is same as equal to 181.4. So let's consider here the triangle C, B and D. This triangle C, B and D. So it is here opposite length is known and a hypotenuse is known. So we can use here sin theta first. So we have sin theta is equal to opposite length is L and the hypotenuse equal to rho. So we have sin theta is same as equal to L. L is equal to 4 meter. So we have 4 divided by 181.4. Naturally this value is very small value. So angle theta will come out to be 1.26. What we are interested is delta max. So we have value of delta max is same as equal to the distance AD. And the distance AD will be same as the distance AC minus the distance CD. AC distance, the AC distance is same as equal to rho, and the CD distance will be the cos. So CD will be same as equal to rho multiplied by cos of theta. Remember here cos is CD divided by rho. So we have rho is taken common here. So we have rho is same as equal to 181.4 into 1 minus cos theta, and we have theta is equal to 1.26. Solve this, you will get your delta max. So approximately we are getting this value is close to 0.044, that will be meter. So we are getting the value of delta max is close to, multiplying by 1000, this answer will be equal to 44 mm. Even the 44 mm is very small as compared to 18,000 mm. A square section as shown in the figure above is subjected to bending moment M. What is the maximum bending stress? We have to find out. The bending moment M is not shown. So let's assume here this is a sagging case. In the case of a square section here, the maximum bending stress will be either tension or compression on the top and bottom fiber. So same point here represent the centroid, and as far as the maximum distance is considered for the top fiber, so for top fiber we have maximum distance C will be same as equal to h by 2, and the moment of inertia is h to the power 4 by 12. So we have m divided by I is same as equal to the value of maximum bending stress, may be compressive or tensile, divided by C. Here you have to take the value of C is equal to h by 2. So we have maximum value of the bending stress will be equal to m into C divided by I. So we have m is a bending moment, C is same as equal to h divided by 2, and I is moment of inertia is h to the power 4 divided by 12. So 12 will shift in numerator. This 12 and 2, so 6 is left in numerator. So we have maximum value of a bending stress will be equal to 6 times m, and one of the h will be get cancelled. So we have 6 times bending moment divided by h cube. 6 times m divided by h cube. Our choice C is correct choice. The beam is shown in the figure is subjected to pure bending moment M. The ratio of the maximum tensile and the maximum compressive stress you have to find out. And the cross section is a triangle whose base is equal to B and the height is equal to H. Now this was the case of sagging, so this value of M you have to take as a positive value. And the axis of symmetry is a vertical in this case. So the centroid will lie on this axis of symmetry, and from the base the centroid will lie at a distance equal to h by 3. So this one is the centroid. From base this distance will be equal to h by 3, and the apex from the centroid at a distance equal to 2h by 3. So we'll fix up our coordinate system through the centroid. Horizontal axis will be equal to the z-axis, vertical axis will be equal to y-axis. So for the top fiber here, we have value of y top will be equal to, is a positive value, is 2h by 3. And since here the base is below the centroid, so y value will be taken as negative, is minus h by 3. So we know the distance of the top fiber and the bottom fiber, and we have flexure formula is m by I is same as equal to negative sigma b divided by y. The bending moment m and the moment of inertia is remain constant here. So the maximum bending stress on the top fiber is sigma b maximum on the top fiber is minus of bending moment m, which one is positive value, moment of inertia is I, multiplied by y of top, which is equal to 2h by 3. Similarly, we have maximum bending stress at bottom is also equal to minus m divided by I, and we have y bottom, which one is negative value h by 3. So we have y bottom. We are interested here the maximum tensile. So first of all you have to identify which one is the tensile here. Now since here the value of y top is equal to 2h by 3 and we have negative sign, so on the top we have a compressive stress and is equal to minus m by I multiplied by 2h divided by 3. And here the value of y bottom for the maximum bending stress at the bottom is negative, negative become positive. So we have maximum bending stress at the bottom is tension and is equal to M into I multiplied by H by 3. H by 3. What we are interested, maximum tensile to maximum compressive. So maximum tensile is at the bottom. So we have sigma tensile divided by sigma compressive will be equal to M by I, and M by will get cancelled. So we have H by 3 divided by 2H by 3. 2H by 3. 3 get cancelled, H get cancelled. So we have tensile stress to compressive stress ratio will be equal to 1 by 2. The video you are watching is from the app, which is the More Class app available on Google Store. And in this app, we'll cover all subjects involved in mechanical engineering for GATE. Join the course directly from your mobile. The link is given here.